Hi, my name is Nicolas, and I'm a research scientist at DeepMind. My academic background is in probabilistic models. More recently, though, I've worked on RL with a particular focus on algorithms for continuous action spaces and motor control. And what I want to do in this talk is share with you my excitement about the progress that the field has made in the last few years. I've recently looked back at my first paper on RL with neural networks from 2012. It includes, as a main experiment, an octopus arm that reaches to a target. By today's standards, this result is really not very impressive. Indeed, it's worth remembering that there was a time pre-DQN when neural networks in RL perhaps did have some successes, but these were certainly much more limited and definitely not as widely known. Looking at this result now makes me feel a bit nostalgic and also a little bit embarrassed. But most importantly, it actually makes me feel excited, because I think it really highlights how far we have progressed since then. Thanks to a number of improvements, including better estimators, better regularization, and a better understanding of ideas such as off-policy learning and experience replay, and of course also due to better engineering, our algorithms have gotten more scalable, more robust, and more data efficient to an extent that they can now solve non-trivial problems in simulation, and that we are also seeing some initial applications on actual hardware. In this talk, I therefore want to look back at where this progress has come from and revisit some of my old papers that I've worked on over the years to see how they've led us to where we are now. But before I begin, I would like to stress that this is going to be a very personal talk. I will focus on papers that myself or close colleagues have worked on simply because I know those best. I will try to mention some of the influential works from the community in passing and also at the end, but I will certainly not be able to do so adequately and do justice to all the amazing work that has happened in the community as a whole. The talk should therefore really not be understood as an attempt of the review of the field, for this it would be far too narrow. Instead, maybe it can be understood as a sketch of my own personal algorithmic history. What I would like to focus on in this talk are algorithms that can solve reinforcement learning problems with high-dimensional continuous action spaces in a data-efficient manner. And I think that most of the successful algorithms that are being used today can be understood in terms of 5 simple ideas. Firstly, learning itself can be decomposed into 2 simple steps: policy evaluation and policy improvement. Policy evaluation means that given a policy pi, we want to estimate its action value function q, which tells us what future reward we can expect if in state x we take action u and follow policy pi thereafter. The second step is policy improvement. Here, we would like to find a new policy pi prime such that the average value under the new policy is higher than the average value under the old policy. The algorithms that I will discuss in this talk implement these 2 steps in different ways and combine them with 3 other ideas or ingredients. Firstly, they may use regularization to control the speed of learning and to improve robustness and reduce the sensitivity to hyperparameter choices. They decouple acting and learning, which gives us flexibility to collect data while following a different policy than the one we want to improve, and also to reuse old data, which can help data efficiency. And finally, and this last point is perhaps less of a concept and more of a lesson that we've learned, good algorithmic principles are not enough. Instead, careful implementation and reliable infrastructure are at least equally critical for good performance. So my personal journey in RL begins in 2012, but the story of the line of work that I want to discuss in this talk begins in 2014 with the deterministic policy gradient paper. This was joint work with a number of people who are all still good colleagues of mine now. The core insight of this paper was that deterministic policies do have gradients and that we can compute these gradients efficiently by backpropagation. The starting point of the line of thinking in the paper was policy gradient RL. And policy gradient RL is in many ways the most natural thing in the world, as it tries to directly maximize the expected reward by gradient ascent with respect to the policy parameters theta here. And a well-known, although perhaps rather surprising result is that we can indeed compute the gradient of the expected reward objective with respect to the policy parameters purely from experience and without any knowledge of the system dynamics. And this is done effectively by adjusting the log probability of actions sampled from the policy according to their Q value. This basic insight by now goes back almost 30 years, and it has been used to motivate a large number of different algorithms, including actor-critic algorithms that approximate QPi with a function approximator. Especially for high-dimensional continuous action spaces, this approach has 2 downsides. Firstly, it effectively corresponds to learning by trial and error. The equation on the previous slide effectively instructs us to trial actions and integrate their values. Secondly, it uses only zeroth order information about the value function, but not its gradients. But clearly, in continuous action spaces, the gradient of the Q function could be highly informative. In particular, it would directly tell us how to change the action to increase the value, and having this information available to adjust the policy could be incredibly valuable. The question that we were therefore asking whether we couldn't do better in settings with high-dimensional continuous actions. Firstly, by using deterministic policies that would avoid the high-dimensional integral over actions, and secondly, by using information about the gradient of the value more directly. The common belief at the time, however, was that a simple form of the policy gradient for deterministic policies did not exist. The main insight of the DPG paper then was that this was not true, and the main result was a policy gradient theorem for deterministic policies. The gradient exists, and it can be computed from experience without any knowledge of the system dynamics. It has an intuitive form, namely that we backpropagate the gradient of the action value function with respect to the action into the policy, and it can be seen as the limiting case of policy gradient algorithms for stochastic policies. It can be implemented efficiently as an actor-critic algorithm that approximates the Q function with a value function approximator, just like for stochastic policies. To make this result actually useful, however, one additional ingredient was needed. Specifically, deterministic policies are not good for exploration. In fact, to be able to learn the Q function in such a way that it can provide estimates of the action value gradient, it is necessary to learn the values of off-policy actions too. To resolve this, we introduced stochastic behavior policies, here denoted by beta, that would explore trajectories around those which the deterministic policy would take. The result was a family of off-policy deterministic policy gradient algorithms that would optimize the value of the deterministic policy for an initial state distribution derived from the behavior policy. And this is basically what's expressed here. So this is a value function for deterministic policies averaged over a state distribution generated by a behavior policy. And this here is the corresponding gradient, where again we average the gradient of the value function of the deterministic policy with respect to the state distribution generated by a behavior policy. We implemented this algorithm in a number of different ways, including variants with compatible features, which were still popular at the time, and applied it to a number of simple control problems, including the familiar octopus arm. Now, the algorithm worked and perhaps showed some performance gains. But what was actually much more important were the conceptual insights, which we derived from the paper. And the DPG algorithm really turned out to be the beginning of a new line of work. Although perhaps a more accurate description would actually be that a beginning had in fact been 30 years earlier, when Paul Verpes and later Ronald Hafner and Martin Riedmiller had already had very similar insights. The next work that I was involved in was the paper on stochastic value gradients with a good colleague of mine, Greg Wayne. And this paper really generalized the insights from the DPG paper. In particular, it took the idea of backpropagation through the value function seriously, and it then derived a number of model-based and model-free algorithms that would be applicable to both deterministic and stochastic policies and systems. And whereas before it had taken us a whole paper to motivate and describe the DPG algorithm, in this new view, DPG emerged as this very simple special case. In retrospect, I've come to realize that the paper was extremely dense and contains too many different ideas to be easily understood. But a very easy way to understand the class of algorithms proposed in the paper is by thinking about the objective as a computation graph. What can be seen on the slide is effectively the computation graph that describes how we compute the value of an initial state as a function of the policy parameters when both policy and system dynamics are deterministic and known. So to do so, we repeatedly apply the policy to produce actions and the system dynamics to generate next states and evaluate the rewards and sum them up. With this picture in mind, we can obtain a very simple algorithm to optimize the objective with respect to theta, namely by computing the gradient with respect to theta by backpropagation. And Just like in RNNs, we obtain a gradient contribution for the parameters from each time step. And this gradient here comes from the current reward, from the influence of the action on the current reward, as well as the influence of the action on the rest of the trajectory. This is the gradient contribution from time step 2, gradient contribution from time step t, gradient contribution from time step 4, and so on. While this works nicely when everything is deterministic and the system dynamics are known, one contribution of our paper was to show that this was still possible when actions or states were stochastic. This is shown here. The basic idea here was to turn the stochastic policy back into a deterministic function, but now a fixed external noise. And we would apply the same idea to the system dynamics. And the same idea was effectively being exploited around that time in approximate inference algorithms under the name reparametrization trick. The result of this transformation is that the graph is now deterministic, conditioned on fixed external random variables, the distribution of which we do not need to learn. And in consequence, we can again apply backpropagation to this graph, just as before. The second question that we addressed was how to deal with the case when the system dynamics are unknown, and more specifically, how learned models can be effectively used to compute policy gradients in this setting. And the final contribution was that we showed how learned value function approximations could be integrated into the scheme. For instance, we can identify the masked part of the graph here with the Q function for time step t equals 2. And this then allows us to replace the graph with a learned function approximator. And this immediately gives rise to an actor-critic algorithm that bears much similarity to DPG, just for stochastic policies. More specifically, to compute the gradient contribution from time step 2 here, we backpropagate from the Q function to the policy parameters, just as we've seen before, through the policy that is conditioned on the external noise that models the stochasticity of the policy. This is expressed in terms of equations down here. So the form that we are seeing is very similar to the one that we've seen before for the deterministic policy gradient, except that we now have an additional expectation with respect to the fixed external noise that accounts for the stochasticity of the policy. And in this scheme, we recover DPG then as a particular simple special case. The overall result of the paper was a family of algorithms spanning from purely model-free algorithms such as DPG and SVG0 to purely model-based algorithms, and including also intermediate ones which backpropagate through the model of the system dynamics for a limited number of steps, like 1 here or k up here, and then use the gradients of a learned value function approximation effectively for bootstrapping. We implemented different versions of the algorithm and tested it on a number of different continuous control problems. So here it is applied to a simple simulation of a swimmer, which we implemented ourselves. These were the times when you would still do this. And here we see the algorithm applied to perhaps more familiar control problems. A monoped, the cheetah, which still exists, and our pride, the algorithm working on a simple bipedal walker. In parallel to work on the SVG paper, colleagues of mine, Timothy Lillicrap and Jonathan Hunt and others, worked on a version of DPG, the deep deterministic policy gradient algorithm, which was particularly simple and effective. This algorithm would end up being very popular. The main contribution was to combine a number of ingredients that had been successful in other settings into an effective algorithm which in consequence showed good results on a broad range of continuous control tasks, both from features and from vision. The most important idea that they integrated into the DPG algorithm was experience replay. Experience replay allows to separate acting and learning and enables data reuse. Instead of training the policy with on-policy data only, data is stored into a replay buffer and can then be reused many times to update the policy. The resulting algorithm was particularly simple. It alternates between 3 steps. Firstly, it gathers data by acting according to a noisy version of the deterministic policies. The transitions that are observed are stored in a replay buffer B. For learning, it then gathers a batch of data, a batch of transitions from the replay buffer, and to do policy evaluation, it performs simple TD0 updates of the value function. To this end, it first computes a target for the value function by summing the reward with the value of the policy at the next step, at the next time step, and then computes the gradient of the squared difference between this target and the prediction of the parametric action value function. To perform policy improvement, it simply follows the deterministic policy gradient algorithm computed for data points in the batch. And to avoid the value function effectively chasing its own tail during bootstrapping, the algorithm, similar to DQN, used target networks. That is, it introduced a second set of value and policy networks, which were used to construct the targets for bootstrapping when learning the value function. These are denoted here by Q pi and pi prime. Q prime, sorry, and pi prime. These target networks are updated more slowly than the online value function, which greatly improves stability. The algorithm also experimented with different advanced network architectures, such as convolutional layers or batch norm. In combination, these different ingredients led to an algorithm that worked really well, both on continuous control problems when trained from low-dimensional feature representations of the state, as well as training directly from pixels. So here are some applications. Very high-dimensional problem back at the time. And here are some results on pixels. Including some examples applying the algorithm to a race car simulator. One important insight from the paper was that simple algorithms could work really well if you got all the ingredients, including the engineering right. The next two papers that I would like to briefly discuss were significant primarily because they highlighted problems often encountered in RL that go beyond the core algorithm. The first paper introduced a large-scale distributed implementation of DDPG, and it further emphasized the dramatic influence that different factors can have on the scalability and data efficiency of all algorithms, including and in particular the exploration strategy. The second paper demonstrated how demonstrations could be used to facilitate learning and provided the first results on actual robots. The goal of the paper by Ivo Popov was to teach a simulated robot arm to stack Duplo bricks. The natural reward for this problem is a sparse one when the two bricks are stacked. However, and perhaps somewhat unsurprisingly, with the sparse reward, the problem becomes very hard to solve, since the algorithm will by chance not normally observe the reward. It simply doesn't stack two bricks spontaneously. In this paper, we therefore experimented with different ideas how we could facilitate the learning problem. We explored both shaping rewards, as well as using episode initializations that effectively corresponded to a curriculum. To this extent, we occasionally initialize the robot arm close to the brick or with the brick already in the fingers. And while the details of the results don't matter so much, what I think is instructive are the two plots shown here. And these show effectively results for 4 different settings of the reward and initial conditions. And these are shown for the same algorithm and evaluation criterion, so they're directly comparable. And even though the latter two are always the same, the performance really varies quite widely. And in my mind, there are 2 takeaways from this picture. Firstly, we need to be very careful when talking about or comparing the difficulty of tasks. Small changes in the learning setup can make a dramatic difference in how easy or hard a task is for an RL agent to find a solution. The second one is that the algorithm is really just one factor among many that determines learning success. And certainly in this example here, it was not the most important one. In the second paper, colleagues of mine explored the question how to teach a robot to perform a difficult insertion task. And loosely inspired by the work described on the previous slide, to overcome the exploration problem, they developed a version of DPG that could deal with demonstrations. This algorithm was as simple as it could be. They simply collected a number of exploration trajectories exploration trajectories where the arm was under the control of a human and then used this data to pre-fill the replay buffer. And since DPG is an off-policy algorithm, it can directly make use of these transitions. And in this case, this greatly sped up learning. So here are some examples of the robot arm being controlled by a human to collect demonstrations. And here are examples of the robot training. And here the robot has finally learned to insert successfully. A third paper that emphasized how we can exploit the ability to decouple learning and acting was the SAC-X paper by Martin Riedmüller and Roland Hafner. This paper leveraged scheduled multitask learning to overcome the exploration problem in sparse reward tasks. And furthermore, it introduced a more scalable and robust version of SVG0. The main contribution of this paper was to introduce the idea of scheduled auxiliary control. To solve difficult sparse reward tasks, they introduced several simpler related tasks of varying level of difficulty. The agent would then learn a separate policy for each of these tasks. And executing these auxiliary policies in the environment in a cleverly scheduled manner then corresponded to an effective way of doing exploration. In making use of off-policy learning, data could be shared across tasks. In particular, the data collected with auxiliary policies could be used to learn the main task. To make this work well, they further introduced additional algorithmic features to make SVG more scalable. For policy evaluation, they added a low variance estimator for k-step returns for value function learning in an off-policy setting. This was basically the retrace operator previously proposed by Rémy Munoz. For policy improvement, they added entropy regularization to the policy update to prevent the policy from collapse. The result was an algorithm that could learn challenging sparse reward tasks in simulation, and that in follow-up work was used to solve a ball and cup task from vision on an actual robot. " 2018 was the year in which our policy iteration algorithms really scaled to larger and harder problems. One of the works that was relevant in this context was the work on distributed distributional DPG, or D4PG. This work introduced several algorithmic changes, including a distributional value function, and it also employed a large-scale distributed implementation. And in combination, these innovations enabled us to solve a number of challenging tasks. The most important innovation of the paper was the introduction of a distributional value function into DPG. And whereas the normal value function models the expected future return as a function of state and action, a distributional value function explicitly models the distribution of the underlying returns. So this is kind of illustrated here. The x-axis is the return value. An important insight derived in a paper by Mark Bellmer is that such a distributional value can be backed up just like the regular value. And this is illustrated here on the left in terms of 3 simple steps. So given the distribution of returns at the next state, to compute a backup, we first apply the discount factor, which shrinks the distribution. We then add the reward, the observed reward, which displaces or shifts the distribution. And finally, because we have a parametric representation of the distribution, we perform some projection step to align the empirical distribution with our parametric form. Importantly, from the perspective of DPG, though, was that distributional values can be easily implemented or integrated into the deterministic policy gradient algorithm. Specifically, the policy update barely changes. We simply replace the gradient of the Q function with respect to the action, which we normally use, with the gradient, the expectation of the gradient of the distributional value with respect to the action, but then perform backpropagation as before. The paper further introduced a pragmatic way of computing k-step returns in an off-policy setting, and also introduced the use of experience replay, which had previously been successful for discrete action spaces. These algorithmic features were implemented in a large-scale setting with multiple actors and a single learner, which is also the configuration that we still use for most of our experiments today. The combination led to a state-of-the-art results on a number of benchmark tasks, both from pixels and from features, as well as very good results on the challenging parkour task that I had worked on before, example of which is sort of shown here. This was really the first time that we had gotten an off-policy learning algorithm to work on these challenging tasks. The second important algorithmic innovation in 2018 was Abbas's MPO algorithm. This algorithm introduced a constraint policy update that greatly improved algorithm efficiency and stability. The important difference between the algorithms that I've described so far and the MPO algorithm is that the policy update is implemented differently. The policy evaluation step remains the same, but rather than computing the gradient of the expected value under the policy with respect to the policy parameters, which is basically what all the previous algorithms have done, the MPO update decomposes these improvement steps into two sub-steps. The first sub-step is the actual improvement itself. Here, we determine a non-parametric policy that improves over the previous policy. This is obtained by fully optimizing the expected value with respect to the non-parametric policy, but subject to a constraint that constrains the non-parametric policy to stay close to the previous policy. The optimal form of this optimization problem is in fact well known, and it corresponds to the old policy reweighted or tilted by the exponentiated Q function. Only in a second step is the non-parametric policy then projected onto a parametric one, again controlling the change in the new parametric policy relative to the old parametric policy. Thus, rather than performing policy improvement in one step, the algorithm first performs policy improvement and then performs neural network fitting separately. Intuitively, we can think of the algorithm in terms of three simple steps. Firstly, given the old policy and associated Q function, we sample multiple actions from the old policy. We then score these actions samples with the exponentiated Q function. And these weighted action samples constitute our non-parametric policy mu. Finally, we obtain the new parametric policy by fitting a neural network-based representation to the weighted action samples via maximum likelihood. The presence of the two trust region constraints really makes this algorithm work very well across a broad range of difficult and high-dimensional benchmark tasks, including ones where the reward changes quite dramatically without the need for any environment-specific hyperparameter tuning. And this is sort of illustrated here for a few high-dimensional problems. 26 action I mentioned here, 56 action I mentioned here. And it also works directly on the robot. Results that we obtained with the MPO algorithm also highlighted how recent algorithmic innovations have not just improved the difficulty of tasks that our algorithms can tackle, but also the efficiency of the algorithms. So here we show some results on the challenging parkour tasks again. And whereas in my previous original experiments with our own implementation of PPO, we needed a large-scale distributed training setup with 128 actor learner machines and ran sort of the experiment for several days. With the new version of MPO, we were able to learn some of these tasks with one actor and one learner in less than 2 days. And this brings me to the end of my review, since MPO, together with D4PG and SVG, are basically the algorithms that we are still using today. Throughout my talk, I've tried to sketch out a number of important algorithmic ideas and other insights that have allowed us to go from a simple region task to high-dimensional motor control problems directly from vision, as well as results on real robots. There are a number of more specialized works that build on the ideas described in this talk that I don't have time to discuss, but I still want to briefly mention. Firstly, the ideas in the stochastic value gradients paper can actually be seen as a special case of a more general family of gradient estimators for general stochastic computation graphs, which we counter in a number of domains. This insight provides us with a general set of tools to deal with hybrid or hierarchical policies, and it also allows us to transfer some of the techniques that are used for credit assignment in RL to other domains, such as approximate inference. Secondly, the algorithms described in this work can actually be extended to work with hierarchical and structured policies or regularized objectives, and we have investigated this both in the value gradient setting and also for MPO. And finally, we've also recently revisited ideas for combining model-based and model-free RL, both in the value gradient setting as well as with stochastic search in an MPO-like algorithm with promising results. To conclude, I would now like to come back to the 5 important ideas or ingredients that I mentioned at the beginning. Through the algorithms that I have presented, I've reviewed a number of different ways to implement each of them. For instance, we have seen different instances for doing policy evaluation, including TD0, the use of different forms of k-step returns, and via a distributional value function. Analogously, the algorithms that I have presented implement policy improvement either via model-based or model-free value gradients, or by using what is effectively form a value-weighted regression in MPO. Different algorithms have used different forms of regularization, for instance, in the form of KL or entropy regularization and using soft or hard constraints. And they have, to different extents, exploited off-policy learning and the separation of learning and acting. We've seen how DDPG uses behavior policies that correspond to noisy versions of the main deterministic policy, and SACX that uses policies that follow auxiliary objectives for exploration. We've also seen how the use of demonstrations can speed up learning. Having seen in practice many different combinations of these ideas, I think we still don't have a clear winner. MPO performs pretty well at the moment, but when adequately implemented, other algorithms are not necessarily that far off. The statement that one can make, I think, is that having some form of regularization is important, and that hard constraints typically work better than soft constraints since they are easier to tune. Beyond that, however, I think it makes mostly sense to think of the ideas presented in this talk as a set of tools or components that can be combined in different ways to obtain good algorithms for different circumstances. For instance, using the distributional value function for D4PG together with MPO-style policy updates can be an effective combination. Specific ideas that early on we thought would be important, such as the use of deterministic policies or, for instance, the use of gradients for policy updates, may actually matter less than we originally thought. Also, the value of learned models is, in my mind, still a bit in the air, although some recent results are quite encouraging. Thus, a second statement that one can potentially make is that actor-critic policy iteration algorithms in general can work well if one takes care to get the details right. And this last point is perhaps one of the most important lessons learned from this work, to pay a lot of attention to the details and be careful with the implementation of any given algorithm. The quality of the implementation and infrastructure and the nature of the networks used are likely to matter as much as the algorithmic principles. As mentioned at the beginning, I do not want to suggest that the ideas described in this talk arose in a vacuum. Specifically, ideas related to value gradient algorithms can be found in Paul Werper's work and in early work by Roland Hafner and Martin Riedmüller. Similarly, some of the ideas underlying MPO are closely related to Jan Peters' relative entropy policy search algorithm. Furthermore, there have been many concurrent works related to off-policy model-free RL. There are way too many papers to fit on one slide, so I'm just highlighting a few of them here. These include combinations of model-based and model-free policy updates, early applications of off-policy model-free RL to real robots, combinations of DDPG with demonstrations, work on hindsight experience replay, which emphasizes the benefit of sharing experience across tasks, improvements to policy evaluation, recent work on model-free RL from vision on real robots, and finally, algorithms such as the soft actor-critic algorithms by Thomas Neuer, which is closely related to the algorithms presented here and has recently been very successful both in simulation and on real robots. And finally, of course, there are other algorithmically less directly related works that have nevertheless been very influential in our thinking. And with this, I would like to conclude my talk. I thank you all for listening. I will leave you with a few fun videos to watch.